The Big Bang Theory has long stood as the foundation of modern cosmology, explaining the origin and evolution of our universe. However, recent discoveries made possible by the James Webb Space Telescope have begun to challenge some aspects of this theory, prompting scientists to rethink what they thought they knew. The telescope's latest image is not only visually stunning, but also has provided compelling new data that has caught experts off guard. This breakthrough has brought clarity to some long-debated questions and sparked fresh discussions about the fundamental nature of the cosmos. One of the key areas of focus revolves around the age of the universe and the rate at which it expands. This problem has been a persistent puzzle for astrophysicists for many decades. Over the past century, tremendous progress has been made in understanding the universe's origins, structure, and ultimate fate. According to the Big Bang Theory, the universe began around 13.8 billion years ago, from an incredibly hot and dense point, and it has been expanding ever since. But measuring exactly how fast this expansion occurs remains a complex challenge. Scientists rely on the Hubble constant to describe the expansion rate of the universe. However, determining the precise value of the Hubble constant is far from straightforward. There are two primary methods used to measure it, and they rely on very different data sets and techniques. The first approach focuses on observing objects in the local universe, such as stars and Type Ia supernovae. These supernovae are considered standard candles because their intrinsic brightness is well understood. By measuring their apparent brightness, astronomers can calculate their distance from Earth, which in turn helps determine how quickly space itself is stretching. The second method involves studying the early universe by analyzing the cosmic microwave background radiation, or CMB. This faint glow of microwave radiation was discovered in the 1960s and is considered the leftover heat from the Big Bang. It originated when the universe was only about 380,000 years old and provides a snapshot of the universe at that early time. By examining tiny fluctuations in temperature and polarization within the CMB, scientists can infer both the age of the universe and its expansion rate at that epoch. Herein lies the problem. These two measurement methods don't agree. Local measurements indicate that the universe is expanding faster than the rate suggested by the cosmic microwave background data. This discrepancy, known as the Hubble tension, has become a major topic of research. Scientists are striving to understand whether the difference is due to unknown physics, errors in measurement techniques, or some overlooked cosmic phenomena. It's a sign that our understanding of the universe might be incomplete, or that new physics may be waiting to be discovered. Enter the James Webb Space Telescope, designed to peer deeper into space and back in time with unprecedented clarity. It has the capability to observe distant galaxies, planets, and cosmic phenomena that were previously beyond our reach. Researchers had hoped that the telescope's data would help resolve the Hubble tension by providing more precise measurements. Instead, the first wave of findings has introduced new surprises that don't fit neatly into existing theories. This suggests that the universe may be more complex than we imagined and could require us to rethink fundamental concepts, such as the nature of dark energy, the mysterious force believed to be accelerating cosmic expansion. Throughout history, each major astronomical discovery has reshaped our understanding of the cosmos. For example, the discovery of the cosmic microwave background radiation in 1965 provided some of the strongest evidence supporting the Big Bang theory. Before that, many scientists believed the universe was static or expanding at a constant rate. However, in the late 1990s, observations revealed that the universe's expansion is accelerating, leading to the introduction of dark energy as a key concept in cosmology. Every new finding forces scientists to revisit old assumptions and build new models that better explain the data. This ongoing process highlights a fundamental truth about science. It is always evolving. New data pushes the boundaries of knowledge, often raising more questions than answers. Although the current discrepancies in measurements present challenges, they also inspire the development of better tools and methods to explore the universe. This excitement about the unknown is what drives cosmologists and physicists worldwide to continue investigating the cosmos. Another related challenge is understanding how matter is distributed throughout space, a concept connected to what is called sigma tension or the Hubble tension. The universe isn't uniform. Some regions contain dense clusters of galaxies while others are relatively empty. Scientists study these variations to understand the universe's structure and how it has evolved over billions of years. One important technique used to analyze this distribution is gravitational lensing, where the gravity of massive objects, like galaxy clusters, bends light coming from even more distant galaxies. This effect helps researchers detect dark matter, an invisible form of matter that does not emit or absorb light, but exerts gravitational influence. By studying the cosmic microwave background alongside gravitational lensing, scientists try to piece together the story of how the universe's early irregularities developed into the complex, large-scale structures we observe today. However, there is a mismatch between what the CMB data suggests about the uniformity of early matter distribution and the clumpy, irregular arrangement seen through lensing observations. This discrepancy implies that something fundamental is missing from current models, likely involving dark matter's role and behavior. According to astrophysicist Adam Rees and his team, the James Webb Space Telescope has been instrumental in refining measurements and theories related to these issues. They initially wondered whether errors in previous measurements from the Hubble Space Telescope might explain the tension, but the James Webb data confirmed the deviations, deepening the mystery. Rees has pointed out that somewhere between these conflicting observations lies a fundamental flaw in our understanding of the cosmos. This revelation pushes scientists to question long-held assumptions and explore new possibilities. The James Webb Space Telescope's sharp infrared vision allows scientists to study cosmic distances with unprecedented precision, giving them new tools to investigate dark matter and dark energy, two of the most enigmatic components of the universe. Although black holes have traditionally been a focus in explaining certain gravitational effects, the influence of dark matter and dark energy on cosmic phenomena is an area of growing interest. Understanding these components better could revolutionize our knowledge of the universe's composition and fate. Each new discovery challenges the scientific community to reconsider previous models and expand the frontiers of knowledge. While this process can be unsettling, it is essential for progress. Understanding the universe is an immense and complex task, but with every step forward, whether it confirms old theories or demands new ones, we move closer to uncovering the true nature of reality. The questions raised by the James Webb Space Telescope's discoveries exemplify how science constantly evolves, propelled by curiosity and the desire to understand the cosmos in ever greater depth.